Hi everyone. Today I want to talk to you about a pretty confusing topic when it comes to using Stan, something called the Jacobian Adjustment. Personally, I haven't had to use the Jacobian Adjustment much in my career, so you'd probably consider this more of an advanced topic. But nonetheless, it's still pretty interesting to learn and pretty useful to know because it gives you some insight into how certain features of Stan work under the hood. So in this video, I'm going to talk about 1, what the Jacobian Adjustment is, 2, how to apply it, and 3, some intuition about why it works. Imagine I have a model with one parameter x and another parameter y, which is a transform parameter and it's equal to the log of x. Now, when I specify my model, I can put a prior on x, let's say a normal 0, 1 prior, and I can compile and sample from that model. The output will give me a distribution of x, which will be a half normal because we limited the range, and also the corresponding distribution of y, which will be a distribution of the log of x, where x is the half normal. But what about if I wanted to put the same prior on y instead? That is, put a prior on a function of a parameter rather than a prior on the parameter itself. So let's try it out. If I put a prior on y and let it run, the code runs with no errors, but once we inspect the distribution, we can see a problem. Y doesn't look like a normal 0, 1, it should look something like what we saw in the previous version, but it looks shifted to one side. It turns out that if you want to put a prior on a transformed variable, you also need to correct the log posterior with something called the Jacobian Adjustment. This is actually quite simple to do, but you do need to know a little bit of calculus. Essentially, you take your transformation, which is y equals log x in this case, and you take the absolute value of the derivative of the transformed parameter with respect to the parameter, that is d log x dx. If you remember your derivative, you might remember this to be 1 on x. The result is called the Jacobian determinant, or the Jacobian for short. Now, in order to complete the correction, you need to add the log of this determinant to the log target density object, like so, and voila! You have now successfully corrected the posterior. If I now run the model and get a distribution of y, we can see that it now assumes the normal distribution we expect. X, on the other hand, takes on a distribution that is the result of the inverse transformation from y. So in a nutshell, the Jacobian correction is needed when you want to put a prior on a transform parameter instead of a regular parameter. In fact, anytime you put a prior on a transform parameter, Stan will spit out a warning telling you need to correct the log posterior with the Jacobian of the transformation. So that's how you do the Jacobian adjustment, but why does it work? Well, the short answer is that when you transform a variable, it will distort the posterior from flat to being curved. Multiplying by the Jacobian determinant will undistort the posterior back to flat again, so you can apply a prior. The long answer will require some explanation. Let's say x was uniformly distributed and I had a variable y that was transformed from x via y equals log x. Now let's ask the question, what does the probability density of y look like? To answer this question, we're going to do a little thought experiment. First, let's plot x and y. We get the following log curve. Now, let's imagine we draw a two-dimensional pipe originating from the x-axis, represented by this grey bar, and based on where this pipe intersects the line, we extend the pipe horizontally to connect to the y-axis. As you can see, because of the slope of the line, the pipe gets larger once we make the left-hand turn. Let's call the width of the pipe on the x and y axis delta x and delta y respectively. Now imagine that at the start of this pipe, at the x-axis, we place some particles, let's say m particles. This represents the probability mass of x in that span of x. The probability density, then, is the mass divided by the width, which is m divided by delta x. Now we let the particles travel to the end and then measure the density at the end of the pipe at the y-axis. Since the number of particles, or the probability mass, stays the same, the probability density at the y end of the pipe is m divided by delta y. Obviously, the same number of particles is in each end of the pipe, but the y-axis has a lower density because the width is higher. We can understand exactly how much it's lower by a bit of algebra. I can rearrange the two formulas and get rid of the m, and then divide by delta x. So the probability density of y is the probability density of x divided by the ratio of delta y and delta x. Now, in the limit, as delta x approaches 0, this tells us that the probability density of y is inversely proportional to the slope of y equals fx. i.e. it's inversely proportional to the derivative dy on dx at the value of x. Let's represent the level of this probability density of y by this red line on a horizontal graph on the left. Now let's repeat the pipe exercise for different values of x and draw their corresponding densities, also in red. Because of the inverse relationship, as x gets larger, the probability density of y goes to infinity, as the slope of log x goes to 0. If we connect the dots with a smooth line, then this line is our probability density of y, which turns out to be e to the power of y. So this explains how the distribution of y is distorted, but how do we undistort it to get it back flat? Well, all I have to do is multiply this probability density by the slope of log x, which is 1 divide x, or 1 divide e to the y. If you do this, I effectively cancel out the division by the slope that the transformation induces, and I recover a uniform distribution. But how is this connected to Stan? Well, in Stan, every parameter declared in the parameters block will be initialized with a flat uniform distribution. Therefore, when you apply a prior in the model block, the parameter will assume a distribution being the multiplication of the prior and a flat distribution, which is just the prior. However, when you have a transformed parameter, then the transformed parameter will be initialized with a non-flat distribution induced by the transformation for the reasons we've explained. So if you apply a prior to the transformed variable without a correction, you will be applying a prior to a non-flat distribution, and the result will be a weird multiplication of the two. So you need to flatten the distribution of the transformed parameter when you apply the prior if you want to recover the prior. This is done by multiplying the posterior by the Jacobian, or adding the log of the Jacobian to the log posterior, which is what this line means. So at this point you might be thinking, that's great, but when will I ever need to use this? In my experience, it's pretty rare to use the Jacobian, but it's still a good thing to know to understand how Stan works under the hood. The reason why is because this is what's happening when you put limits on your parameters. For example, if you limit a variable to be strictly greater than 0, like in this Stan file, you could actually accomplish this by transforming the variables to e to the x and then adding the log Jacobian to the target. One of the great features about Stan, though, is that you don't actually have to see any of that. You just need to specify the limits in the declaration and the Jacobian gets applied in the background. Well, that's it for Jacobian transformations. I hope you liked the video, and if you want to learn more about Stan and get more practical examples of how to use Stan in real life, check out my tutorial series, Bayesian Inference with Stan. Don't forget to sample that like button, hit subscribe for more awesome Stan content, and I'll see you in the next one.